cartoon, or it might be a real picture, as in this case. And this is why rulers might be very important. Ms. Baker said you've only needed a ruler once in all of her experience. But if this comes up, oh, you need a ruler. And unless they give you a little ruler on the page, which I'm guessing they won't. And from that, the concept, I mean, if you can think about it, you should be able to reason out how to do these calculations. But they're going to give you a size on the page. They're also going to tell you how much bigger that thing is on the page than in real life. So for instance here, this bacteria is 15,000 times bigger than it ought to be. So how do you figure out how big it really is? Take its size, divide it by 15,000, right? Pretty straightforward. That's its actual size. If it's 15,000 times bigger here, we'll figure out how big this is and make that 15,000 times smaller. What you might need to do is play with the units a little bit, which is why it's a good reminder that micrometers and millimeters are a 1,000x difference. You move the decimal place 3 times, and if you're not sure which way to move it, try moving it both directions and see which one makes sense. Is 0.003 millimeters the same as 0.000003 micrometers? No. There's 1,000 micrometers in every millimeter. So to me it would make more sense to move it the other way and go, oh, 0.003 millimeters, that's about 3 micrometers. So that's how you do actual size, just the length of it on the page over how much it's been magnified.
Is it just 3 decimals?
It's 3 places. It's 1,000 times. So, and then of course there's 10 millimeters in a centimeter, so you might need to move it one more time if you measure in centimeters. But I usually measure in millimeters no matter what. The other thing they might ask you to do is to calculate how much something has been magnified, which is sort of the same process, just flipped around a little bit. But here's where it might be important to know that if you're doing magnification, there's a little bit of unit cancellation, because magnification does not have a unit. It's an x, right? So, in the case of magnification, they are not going to give you necessarily how much it's been magnified. That would be the answer, right? They're not going to say 15,000x or 20x or whatever. But what they will give you is a scale bar. Oh, you guys remember the scale bars? Oh, I always remember the groans from the students when I show these. So here's really the biggest pitfall with this one. Folks, like actual size, take their ruler and they put it on the bacteria. It doesn't matter how big the bacteria is. It doesn't matter. It really doesn't. Or in this case, it's a mitochondria. It makes no difference. There could be a smiley face right here. Don't measure it. There could be Abraham Lincoln's top hat. Don't measure it. It doesn't matter what anything in this picture is, because everything in this picture has been magnified the same amount. And there's only one thing in this picture you actually know how big it used to be. The scale bar. You know that that scale bar used to be 2 micrometers and now it's bigger. So that's what you measure. A lot of people measure the other thing. Nothing else in this picture matters. There literally doesn't even need to be a picture. There just needs to be a little scale bar. And the rest of this could literally just not exist. You can still get the answer. So you measure the scale bar and you get a size. In this case, we're going to assume it was like 30 millimeters. And then the scale bar actually says 2 micrometers. And here's where the units come in. You cannot divide millimeters by micrometers, right? So micrometers go up by thousands, and then you've turned them into millimeters. 2 micrometers? How many millimeters is that? A lot or a little? A little. So move the decimal place, so that it becomes littler. 30,000, or rather, sorry, in this case I actually did the other one. You could also turn millimeters into micrometers, so 30 turns into 30,000. Either way, if you move that decimal point or if you move that decimal point, as long as you get them into the same units, it does not matter which one you do. Units cancel, and you get 15,000x. So there you go. You would get a very different number if for some reason you measured the mitochondria, because that has nothing to do with the scale bar. The scale bar is the only thing that matters. Yes?
Shouldn't you get it in the same, because it says 2 micrometers, shouldn't you get it in 2 micrometers so it matches with the picture?
They are asking for magnification.
Yeah, with when the magnification, open the memory.
With magnification, your units cancel. So, I mean, you could turn this into millimeters, you could turn that into micrometers. It's going to get the same answer either way. And the units would cancel either way. Cool. Here's like an example. What is the magnification of the egg? What is the actual size of the egg? You need to find one of them first. Which one?
Magnification.
Yeah, magnification. 40 micrometers right there. So you measure it on the page, see how much bigger than 40 micrometers it is. That gives you the magnification. Then using that, you measure the egg, and then divide it by magnification. You get the answer. Yeah?
Calculator on this test, or is that not?
This would be on paper 2, and I think you get a calculator on paper 2. And paper 3.
Yes. Miss Baker says
I would bring your own. Not on paper 1. But again, the only things I could imagine them asking you to do on paper 1 would be this sort of stuff. Like, a cell is, they might make this into a word problem on paper 1, and then you'd have to just work it out. You're not actually measuring anything. But yeah, micrometers and millimeters are 1,000x apart, and using that you should be able to reason most of these things out. Okay, here is the second lab practical. If you remember the estimation of osmolarity, you guys remember osmosis and all that stuff? Okay, in osmosis, water moves across a membrane from
high to low. Solute.
solute. Tell me about the solutes.
It moves from low to high solute.
From low to high solute. Or, what's the name for a low solute area?
Hypotonic.
Hypotonic. And then the one with a lot of solute is hypertonic. Until they are equal or isotonic. Okay. So, we framed this lab as Mr. Potato Head needs an organ transplant. And just as with real organ transplants, if you put that organ into a hypertonic situation, then the water is going to leave that organ, go towards hypertonic. It's going to shrivel up. If you put the organ into a hypotonic situation, well then the water is going to seep into the organ. That's not good either. You don't want your organ changing its osmolarity, or rather, the concentration of solutes per amount of water. So what we did, and this is like a word problem that I created that kind of helps sort of parse out some of these concepts. But here's an osmolarity-ish problem. A population of sea slugs is going to be placed in aquariums, each with a different solution for water. Water solutions had different amounts of dissolved salt. 0 molarity, 0.1, 0.2, 0.3, 0.4, 0.5, and 0.6 molarity salts. So in other words, saltier and saltier and saltier and saltier. The mass of each slug was taken before and then after, and then here's the percent change in mass. Slugs that were put into pure water, they got bigger. Does that make sense? Because there's more stuff in a slug than pure water. So osmosis would bring the water into the slugs. 0.1, they grew, but not by as much. 0.2, they grew, but not even by as much. 0.3, they grew a little. 0.4, they almost didn't grow at all. In the salty-ish water, they shrank, and then in the really salty water, they really shrank. So there's a trend here, ladies and gentlemen. How do you know the osmolarity of a slug? Whatever solution to put them in, they would be isotonic to. Well, that osmolarity is their osmolarity. So up here, if you're kind of estimating that if you put them into a solution that was like 0.42.
Alex Wynn, call 5604.
That would probably be their osmolarity. That would be a solution in which they are not gaining water and they are not losing water. All right, enzyme design lab. Remember doing these?